So let's start our lecture 2. We will be starting from where we left off in the last class. We discussed in the last class about the atomic structure, and we discussed that any electron can only have the discrete values of energy. Yes, it cannot take up all the available energy with it. And we discussed that there are certain energy levels which we denote by 1s, 2s, 2p, 3s and 3p. Okay, so these are the energy levels. Now we discussed about how the electrons are going to fill up these energy levels. Now in order to fill up these energy levels, we need to follow the Pauli exclusion principle, okay, which says that no two electrons can occupy the same quantum state. Okay, so it's like the parking area. No two cars can occupy the same space. Yes. So we discussed that this 1s energy level can only have the two quantum states, so only two electrons can be there. Similarly, for the p orbital, we discussed that there can be 6 quantum states possible, so only 6 electrons can be occupied. Yes. Now in this manner, we filled up these energy levels for the silicon atoms which have the 14th electron. Yes, and the 3p energy level can have the 6 quantum states, but only the 2 electrons were remaining to fill up, so the 4 quantum states would be empty. Okay. Now the question is, what happens? So this was the case for the single atom. Okay, so this was the energy configuration for single silicon atom. Now what happens when you bring up two silicon atoms together? Okay. Now I want to ask you, so this is kind of a molecule, okay, molecule. So when you take up a molecule with having two atoms, will the configuration for each silicon atom be the same? So I am asking, let's suppose this is the same configuration. This is our second atom, okay, and this is the same energy configuration we are having for the silicon atom, second silicon atom. Now, is this possible? This energy configuration will not be the possible for the second silicon atom. Why? Because if this energy configuration is possible, then this electron and this electrons would be having the same quantum states. Yes, because this is also 1s energy level and this is also 1s energy level. Now these two electrons would be having the same quantum states, but the Pauli exclusion principle says no two electrons can occupy the same quantum state. Yes. So now this is the problem. How these energy levels are going to be defined for the two atoms, or for the matter, how these energy levels are defined for the larger number of the atoms. Okay. So what happens when you bring up two atoms close together in the close proximity? So what happens? This single energy level is going to split up into the two energy levels. Okay, so just see this fact. Before, the 1s energy level is going to have the one, this is the single energy level, okay, and you can occupy 2 electrons in this energy level. So this is the case before, but after when you take up the 2 silicon atoms together, okay, so this is the case for the single silicon atom. When you take up the 2 atoms together, what happens? This 1s energy level is going to split up into the 2 energy levels. Okay, so we also call them 1s star and 1s. Okay, so these are the bonding energy level and the anti-bonding energy levels. We are not going into the detail. This is enough for us. So what happens? This single energy level is going to split up into the 2 energy levels. Okay, now the Pauli would be happy because we can fill up the 4 electrons, because each 1s level for the single atom would be having the 2 atoms. So now the 2 atoms can fill up their electrons in the 2 energy levels. Okay, so now the Pauli exclusion principle is consistent with this rule. Yes, so we are consistent with the Pauli exclusion principle rule, and this is what happens. So the single energy level splits up into the 2 energy levels. Okay, Similarly, this 2s energy level would also be splitting up into the two energy levels. Yes, for the 2s it would be the same. So for all energy levels it would be the true. All the energy levels will be splitting up into the two when we are taking the two atoms together. Similarly, what will happen when we will bring up a large number of atoms in the close proximity, very close to each other? So what happens? These energy levels, so let me draw here. So this single energy level is going to split up into the multiple energy levels. Okay, so this is how this single energy level is going to split up. So okay, so for example, in the silicon crystal, there are 5 into 10 to the power 22 atoms per centimeter cube. Okay, so this is the atomic density for the silicon crystal. Now, when we are taking the 5 into 10 to the power 22 atoms together, these single energy level of 1s, or for example 2s, 2p, are going to split up into 5 into 10 to the power 22 energy levels. Okay, so this single energy level will be going to split up into the large number of the energy levels. And if you can see, these energy levels will be so close to each other that you cannot distinguish it with the band. Okay, so we also call, so like this, these energy levels will be splitting up, and this is like a band of the energy levels. Okay, so the gap between these energy levels is so small that you cannot figure it out. Okay, so we kind of treat it as a continuous band of the energies. So it is like a continuum. These are no more discrete levels of the energy. These are the continuous energies. So from, let's say this is E1 and this is E2. From E1 to E2, electrons can take up any energy levels. Okay. So now let's talk about one important thing also. Let me remove it. Okay. If you can see, when you will bring up the n atoms together, so for the single atom, this is having the two quantum states available. Yes, so there are two quantum states available. For the n atoms, this 1s would be splitting up into the n energy levels, and these n energy levels, so let me make it, so this would be kind of n energy levels. Yes, so this would be kind of band of the energy levels, and there would be 5 into 10 to the power 22 energy levels. Okay, so just to make you understand, now this band would be having the 2n quantum states. Yes, 2n quantum states would be there, because each single atom is going to have the two quantum states, so the n atoms would be having 2n quantum states. Similarly, this 2s would be having 2n quantum states, 2p would be having 6n quantum states, 3s would be having 2n quantum states, and the 3p would be having 6n quantum states when you will bring up n atoms of silicon together. Yes, so this will be transformed into the band. Yes, so let me fill up this. So these are the still discrete energy levels, but we cannot distinguish the gap between these levels, so we are kind of treating them as a band of the energy levels. Okay, so these would be 6n. Now this band would be having the 6n quantum states available. Okay, now for each single atom, there were only the 2 electrons available in the 3p states. Yes, so there are possible 6n quantum states available, but we are only having the 2n electrons available. Yes, so 2n electrons and 6n quantum states. Similarly, for 3s, all the quantum states would be filled, so 2n electrons and 2n quantum state. Okay, similarly these lower quantum states would be filled completely. So now let us talk about only the valence cell. Okay, so these are the outermost cell, 3p and 3s. These 2p, 2s and 1s would be so close to nucleus that they would not be the responsible for the conductivity or the chemical reaction in the atoms or in the crystal. Only the 3p and 3s, which are the outermost cell or the outermost orbitals, would be only responsible for the chemical reaction. So let's talk about the 3p and the 3s. Okay, so in the side, let me draw this. So we would be having like these two bands. Okay, now we would be having the bands when we are talking about the n atoms. So let's say this is our 3s. Okay, and this band is our like 3p band. Okay, now here in the 3p, 6n quantum states are available, but 2n's are filled. Yes, only 2n's are filled, and in the 3s, 2n states are available, and 2n's all the states are filled. Yes. Now let us see a diagram which I have taken from the book. So initially we are having this picture. In the 3p state, we are having the 6n states and 2n electrons are available. So the 4n states are empty. And in the 3s, we are having the 2n states and 2n electrons are there. So these 2n states are completely filled. Now what happens when you bring up these n atoms very close to each other? So kind of if you decrease the distance r, interatomic distance, if you decrease, these bands 3p and 3s bands will be further splitting up and would be kind of merging up with each other. Now these 2n electrons which are filled are going to merge into this 2n states. So there would be 4n states available now in the below part, and the 4n electrons would be there. So the below area, this below area would be completely filled. Now the remaining 4n states which are empty here would be going into the upward direction. There are no electrons, 0 electrons are there. Okay, so now this is what we call conduction band, and this is what we call valence band. Okay, and this is the energy gap between these two bands. So we draw for the understanding like that. This is our valence band, okay, which is completely filled, and this is our conduction band, which is completely empty. At 0 Kelvin we are talking about. Okay, there is no temperature till now. So this is completely empty. Okay, and this is filled completely. Okay, so now from here on we will be discussing our EDC, that what is the valence band we now know, what is the conduction band we now know. Now what happens when we will be increasing the temperature, how the free electrons will be moving from valence band to conduction band, this theory we will be building up in the next lectures.